this should work now. So far.
Can I send you a presentation to show on while we're waiting for the first speaker?
Sure.
I mean, why would you not use the laptop that's connected there instead of this? Well, they used to be. This one certainly isn't. Yeah, it's live now. This one certainly won't be connected to the projector. It'll be connected to nothing.
Can you check it's live?
Like as in the first speaker.
That's the channel, right?
Here, boom, live.
It's fine, we can put up like a display.
What? It's just live on there.
Let me try restarting YouTube, maybe that's an issue.
Yeah, we are. When the first speaker is
Try and find times.
Yeah, it works on the. Shows up? It works.
The other thing I was going to say is, John's not going first. The other speaker.
Yeah, you see it. Sure. I think yeah, John can go first.
Wait, we're changing the running order now. Because we didn't have it that way. Last time we had it, at least the way we announced it was that the other speaker was first, right?
We didn't announce the running order.
But their name came first. It's whatever. Fine.
I switched out of the email too. I know.
Fine. Do you have a I think Sigyn wanted to show something on there.
How many for Lori?
Your laptop is charged, right?
I think you can restart.
There's a charger in the presenter's desk, so you can bring the cable over.
And there's also a port right in there.
Right, sure, whatever.
There's a microphone somewhere. Is this?
Oh, do you want a microphone?
I don't mind. Do you want me to have a microphone?
Yeah, no, of course you need a microphone. Sorry.
Yeah.
There you go.
Brilliant. Okay. This is the.
I think it's muted.
This is recording.
This is my microphone.
Yes, perfect. This is not one. Actually, that's one. It's better.
I think one of these was on and there's like really sound in the last thing.
It was not the fault of the microphone. What was the? Because the sound was in both AT and DID form. There's some issue.
It was so annoying. It was driving me crazy.
by our talk sets for just a minute or two. I mean, this one seems like once we just finalize some answers that we had said. Which is hang on.
Thanks very much. Okay, so thanks very much for the invitation. I'm going to try and talk about, give an idea of the research area that I myself work in. So I don't often get a chance to do that to undergraduate students, so I'm particularly pleased to have this opportunity. I also want to say I'm dead impressed by you guys organising all these events, and I thought the TypeSig conference last week was just awesome, so really impressed by it. Yeah, and I understand your work. thirst for learning about programming languages. So hopefully this will feed into that a bit. Just to maybe help me pace it, can I ask, is there anyone here who is in their first year? You're in your first year, okay. Just one. Who's in the second year? You're in the second year, so you're doing my course at the moment, and the rest of you, I guess, are in higher years. That's hopeful. Okay, so there may be a few things that sort of just wash over if you're in your first year, but hopefully okay. So, the question I want to talk about is, are all programming languages equally powerful? So, as we know, there are zillions of different programming languages out there, and you've been learning about some of them. And they come in different styles, which it's not a clear-cut division, but there are sort of different idioms or different paradigms for programming languages. So there are imperative languages, where you basically go through a sequence of instructions, and that's fairly quite close to the sort of machine-level model of what's going on. So languages like C are not too far from machine code, compiled very quickly. Object-oriented languages, they tend to be imperative languages with another layer added on top of objects. You know all about those. And then quite different in spirit are functional languages, and Pascal is one that we all have seen. And there's various other things that I don't know so much about. So there are, it's obvious that there are major kind of stylistic differences between these styles, these kinds of languages. And for certain practical purposes, you know, people argue that some language might be better than another, or one kind of language is easier to reason about than another. And there are even these kind of ideological differences. So you're probably aware people become very attached to one or other of these ways of thinking, and they will argue for it passionately. Maybe some of you argue for yourselves about this. You do, yeah, okay. So, for example, there's a certain religion of functional programming, if you like, whose sacred symbol is the lambda. Right? So if you see anyone wearing a lambda, that's a fairly sure sign that they subscribe to this religion of functional programming. Okay. So people, there's all these differences at various levels. But what I want to ask today is, well, do they differ in even more fundamental ways than these? In other words, well, that's a typo. Okay, so to say, are they all equally powerful in some way, fundamentally, in terms of what you fundamentally can do in each of them? You know, never mind how convenient it is or easy it is. There's some sense in which they're all kind of the same, really. Okay, and as we'll see, there's some interest in discussing this question because we can make this question precise in different ways, and the answer to this question will depend on what exactly we mean. But I'm looking at fundamental differences, not sort of surface differences of style. What might we mean by equally powerful? Okay, so one thing we might be talking about what is possible, what is and isn't possible to compute in the different languages. So for instance, what mathematical functions, say, is it possible to write a program to compute? So do all languages agree on what they can compute in principle? Okay, so never mind how efficiently they can compute it, never mind the limitations on time and space or something. Do they all fundamentally agree in what's computable? Or do some languages let us compute things that simply wouldn't be possible at all in other languages? That's one kind of question you can ask. Or you can ask a question more on the complexity side. So, if they can all compute the same things, for instance, do they all agree in the fundamental efficiency with which they can compute things? Okay? Or do some languages actually let us do certain things more efficiently than others? And by more efficiently here, I mean not just efficient and faster by a factor of 10 or something like that, but more efficiently in a fundamental way, in the sense of asymptotics, which is a word you've heard me use quite a lot, probably most of you. It's a scary word, I know, but can we do some things asymptotically faster in some kinds of languages than others? So if there were differences of either of these two kinds, I think we would regard that as an interesting fact that we would want to know about. So we'll consider both of these questions, and we'll consider each of them in two settings. First of all, we'll look at the situation for what I call bog standard computation. So by bog standard computation, I mean basically you've got a program that takes an input, delivers an output. And both the input and output are basically strings. Okay, they're basically finite sequences of symbols over a finite character set. I mean, there might be a file that you read in, an input file and an output file. The file is basically a finite sequence of characters. Okay, so that's the bog standard setting where the inputs and outputs of this very simple kind of flat kind. Or we can ask the question in a setting where inputs and outputs can be more subtle kinds of things. So, for instance, we might have a function whose input is itself a function of some kind, a higher order function. Or it might be an object, as in an object, in the sense of object-oriented language, with an object with methods you can call. Or it might be a process of some other kind. Some data of some kind of more dynamic kind than just a simple flat string. Okay? And as we'll see, this is a more interesting situation than the bog standard one. So what I'll do is I'll look at all four cross combinations of these. We'll start with the bog standard one, and we'll summarise fairly quickly what the situation is for both computability and complexity. And then I'll look at the higher order picture, and I'll give you some examples again of both to illustrate some of the strange things and interesting things that go on there. Okay, so what's the classic story for bog standard computation? So those of you who are in second year, you're going to hear me talk about this in my last two lectures of IADS in just a few weeks' time. Okay, so we're talking about finite sets of strings. So as is traditional, let's write sigma for our alphabet, our set of characters, and sigma star for the set of finite strings over sigma. Okay, so these two dudes here who worked in the 1930s, they more or less independently arrived at a major discovery, which is that there's a certain class of functions, say from strings to strings, which can be computed in a mechanical way. So we're not completely ignoring time and space limitations here. Okay, we're saying what can we compute in principle given unlimited time, unlimited memory. So they identified a mathematically defined class of functions called the Church-Turing computable functions, which are nowadays pretty much universally accepted as coinciding with the functions that can be computed by mechanical or algorithmic means. Okay? So we can think of these as going from strings to strings, or equivalently, well, you can translate easily enough between strings and potentially very big natural numbers. Okay, I mean, any natural number has a decimal representation, which is a string. For any string, you can regard as a very long binary number, if you want to, something like that. So there's no really interesting difference between strings and natural numbers in this setting. And basically, all programming languages that are worth their salt at all agree insofar as they can compute exactly these functions known as the Church-Turing computable functions. Okay? So we don't see any, if we're talking about bog standard computation, we're talking about computability, we don't see any interesting differences between one programming language and another. Okay? So there's really not much to say there. This is the standard picture that most people know about. Now, just as a little digression, it might be philosophically interesting to ask, well, this is what our current computers can do, but could there ever be a physical computing device, perhaps based on some wacky kind of physics, maybe even some physics we don't know about, that lets us break this barrier? Could there, 1,000 years in the future, be computing devices that allow us to compute things that are not currently Turing computable? So there have been some very wacky speculations involving sort of jumping into black holes and things like that. Okay, which suggests that if you prepare to go to these ultimate extremes, the universe we're in might, in principle, allow us to compute non-Turing computable things. And that's all kind of amusing and entertaining, but I'm not going to go there today. So just to mention, so we can take it as read that this is the standard of what's considered mechanically computable in the bog standard setting. in the bog standard setting, can we do some things more efficiently in some languages than others? So another way of thinking about what we've been saying already is, broadly speaking, any decent programming language would have what it took to simulate any other programming language. So, for instance, you can write, you've got Java and Python, let's say. You could, within Python, within Java, you could write an interpreter for Python and vice versa. So each language can simulate each other. In particular, if your language P has mutable arrays, okay, just arrays where you're allowed to update the value of each cell, you can just start by creating a big array that's going to play the role of the program memory in the language you're trying to simulate. Remember that with the stack and the heap and all that stuff. Okay. So you just make a big array, pretend that's your program memory of Q, and you could simulate, you could step through any program. Is this first stop? No. Oh, it's dropped. Okay. Okay, is this? Yeah, that's okay. I'll hold it because it takes me 5 minutes to get it on holding. Okay. So you could sort of step through the execution of a Q program using a P program as an interpreter. And that might not be very fast, that might run much, much slower than a native or sensible implementation of Q, but probably it's only going to be slower by a constant factor, maybe by a factor of 20 or 100 or something, but only a constant factor. So it's still not going to see any fundamental, in the sense of asymptotics, any efficiency difference between P and Q, because everything we can do in P on our functions and strings, anything we can do in Q, we could do in P, just by with a constant factor slow down. That's broadly the picture, but there is an interesting question here. I've said you can do this if you have mutable arrays. But supposing you're in a very pure functional setting where you don't have mutable arrays because you don't like mutable state. Right? It's against your religion. Okay. So pure. I just want to throw out a question here. I don't actually know the answer to this, and I've not seen it discussed. But it's just so. Is it true that you can, even for bog standard computation, are there things that you can't do in Haskell with the asymptotic efficiency that you can do in other languages? So, for example, those of you who are doing IDS or have done it will have seen this coin changing problem. Okay, we're given a set of coin values, and this is the set of coin values we have here, and a number n, and we're asking how many ways is it possible to make up n from combinations of these coins. So if you think about it, if n is 5. There's 4 ways to make a 5 out of these combinations. Okay? And there's a classic solution to this using dynamic programming, which you will know about. And that's very nice. Okay? And this dynamic programming language, it makes use of arrays. Okay? And it makes use of the ability to update these arrays. Okay? And you can do this, for those of you who know what this means, in any language with where you've got mutable arrays, you can do this in time linear in n. Okay? I don't actually know, can this runtime be achieved in pure Haskell? We certainly can achieve it with an extra log n factor here. Do you know the answer to this?
Does pure Haskell exclude the functions that you picked as unsafe?
Yeah. Okay. So interpret pure Haskell. Yeah. Pure means safe. Yeah. I mean, interpret this in such a way to make this an interesting question. I mean, and I might not even have got exactly the right problem here, but there's something here. I mean, the method I can think of, there are ways of simulating kind of, mutable store or something using trees and things. There's sort of functional versions of lookup tables and things, but they tend to introduce this log n array. I'm just intrigued. This seems quite a fundamental question, and I've not seen it asked before. So,
I suspect if Haskell had a problem like that, no one would use it.
Well, I know you talk to Haskell people. They say, well,
I suppose no one really does.
These might be quite obscure. They're willing to accept log n over. I mean, in general, there are functional implementations of various data structures that are less efficient than the standard ones by a factor of log n, and people, the functional programming guys buy this.
I mean, there's a lot of cases where asymptotics just don't matter.
Yeah.
For sorting.
Sure. Yeah, it's just, I mean, I'm not saying whether this matters or not. I'm just saying it's interesting that there's this quite fundamental question that's not in here. So, but anyway, apart from that, so at the kind of, you know, at that end, this very pure end of the spectrum where we don't even have mutable state, there's a little question that arises here. But otherwise, we don't see differences between one language and another. That's what I'm saying. Everything sort of can simulate everything else. Okay. So that's the bog standard story. So now what about higher order stuff? Okay. So I'm going to show you just a selection of three kind of strange things. Right? Just to illustrate that things can be more subtle. Okay. So the first strange thing is this. Suppose, to start with, we're in Haskell and we want to implement just a logical OR operation on Boolean. So we take two Boolean arguments and we want to return a Boolean. Okay? That might seem very, very boring, but remember that Haskell is a lazy language. Okay? So when you pass an argument of type bool, in general that argument needn't be actually just a straight value, like true or false. It's something more like a program that you can there's a term you can evaluate if you like, and it may return true or false. Or it may not, it may never return. Okay, the evaluation might be undefined, it might just run forever. So what we're passing in here is not the kind of flat data you represent in strings. It's something more, the arguments are more dynamic. They're like a little box. I give you a little box with a button you can press if you want to, and if you press the button you might get true, you might get false, or nothing might happen. Okay. So what would we like so bear in mind there's three possibilities. What would we ideally like our OR function to do? Okay. Well, if one of the arguments is true, okay, then we want to be able to return true whatever the other argument is. Okay. So if the other argument is true or false, or even if the other argument is undefined, goes undefined, it doesn't return. Okay. If just the fact that one argument is true should be enough to allow us to return true here, ideally. Okay. And likewise, if the other argument is undefined, we want to return true here. It's only if both arguments have returned and they've both returned false, then we can say it's false. Okay. If we have false here and we're waiting for a result here, then we can't give we have to wait for this to give a result before we can give a result. So this would be the kind of best truth table we could hope for. Okay. So a little question is, can we write a program to do this in what we might call pure Haskell, suitably construed? And by this, I mean without recourse to specialist libraries that aren't sort of there part of the definition of the Haskell language itself. Okay, does anyone, so I'm interested, does anyone have any intuitions on this?
Yes.
You think we can?
Yeah, you launch a thread for each time. And then
Sorry?
so you evaluate each argument on a separate thread.
Right, so threads, okay, but threads are outside what I mean by pure Haskell.
I assume because they're in the standard library that it would be.
Right, so there's a concurrent, okay, the question, this is exactly the point, okay. So, so there's a fairly widely used concurrency library for Haskell, okay. But if you look at, there's a definition of Haskell itself. Yeah, that's not there. So what's the issue here? So what I mean by pure, but thank you, you're exactly thinking the right way. So what I mean by pure Haskell, this is an example of something that actually just can't be done. At least if we want the type of our OR to be this bool and bool and bool. In other words, we want to be able to accept any arguments of type bool and do this. So what happens if we try? So here's an attempt which I call left OR, because here we take these two arguments and we evaluate the left one first. So if x evaluates to true, then we can return true, whatever. It doesn't matter what y does. Otherwise, we have to evaluate y. Okay. So if we run this with the first argument true and the second argument something that loops, this will return true because we never get as far as this y. But if we run it with a loop as the first argument, then, oh dear, okay, we loop, whereas we'd like to be able to return true. Because the second argument is true, only we never discover that, okay? Or you could try it the other way around, you could try it with the right or, try running the second argument first, and then you run the risk that it's the first argument that's true, and you never discover that. So the point is, in this sort of very pure version of Haskell, you've only got one life, okay? And you can use that to evaluate either run of the arguments. But then, if that argument doesn't return, then you've used up your life, and there's nothing you can do, okay? So if we want an OR function that does implement this truth table, we need some kind of concurrency, some kind of thread, multiple threads, or something like that, which many languages support. But the point is that this has highlighted an interesting computability difference between different kinds of languages. So there's an interesting distinction here between what we might call sequential or single-threaded languages and concurrent languages. So both these family languages are indistinguishable in terms of what they can compute in the bog standard setting. They're both Turing complete. You know, you don't see a difference in the bog standard setting. But when you look at this more subtle data, and this is a very simple example of higher order data, you see that there's actually some difference, a fundamental difference between what you can and can't compute. So that's a curious and interesting thing. Now note of course that we've got these two programs given as arguments. Of course, if we were given the source code of those programs, we'd be able to step through them in a sort of interleaved way and see if either of them are ever terminated. But that isn't how they're given to us if we're working with a thing of this type. We're not given these arguments as source code that we can inspect. We're given them as just as a box with a button we can press or not. So there's something crucial, sort of the moral here is that it really makes a big difference how the data is given to you in this higher order setting and what means of interacting with it you have. Okay, so this already shows us that things in this higher order setting are not as simple as in the bog standard setting. There isn't just one universal notion of what it means to be computable. There are different languages embody different notions of computability. Okay, second strange thing, quite different. We're going to talk about the difference between iteration and recursion. Okay, so you all learn early on that there are there is two styles of implementing something like a factorial function. So here's how it would look using iteration. You've all seen stuff like this. You just have a loop here and you multiply everything in. And here's a recursive definition of a factorial function. So they look quite different. So I'm genuinely curious to know, actually, which of these do you think is easier to understand? So who thinks this? Who finds this easier to understand than the other one? Yeah. Interesting. Who finds this easier to understand? It's about the same. That's quite interesting. So yeah, this maybe reflects the kind of there are these cultures. But hopefully you understand. You actually will understand both of these. Fine. Okay. Now we often think of these as just kind of two styles or two ways of doing basically the same thing. I mean, they're ways of doing looping, aren't they? It's kind of maybe think it's only a stylistic difference. But is it really just a stylistic difference? Are these two concepts or these constructs really equivalent in a deeper level? So what we'll see is it turns out that in a higher order setting, recursion is definitely more powerful. Okay? So again, there would be a genuine computability difference between a language that had iteration but didn't let you do recursion and a language that let you do recursion. Once you can do recursion, you can sort of define any iteration construct you like quite easily. So there's, in principle, a genuine computability difference between different kinds of languages. Now, in practice, it's a rather artificial example because I don't know of any widely used languages that don't allow recursion in practice. So it's only, if you know anything, it's only, in theory, one can imagine a theoretical language which with iteration, which again would already be Turing complete, but it would be weaker than the language with recursion in the sense of the way I'm about to show you. Okay? So here's a wacky thing you can do with recursion that you can't do without it. And this is really quite counterintuitive. So, right, so the surprising thing is it is sometimes possible to do an exhaustive search over an infinite data type. Okay, now this might just seem completely crazy, but there can be data types with infinitely many possible values, such that you can ask the answer questions like, does there exist a value of this data type with some property? Okay. You may not believe that just yet, but hopefully you will in a few minutes. Okay. So yeah, here's some Haskell code. So you can do this in Haskell. So we don't need any other. We've got recursion. We don't need any other much else in terms of language features. So the data type we're going to do searches over is the data type of lists of booleans. And remember, these are lazy lists, so these are potentially infinite lists of booleans. Okay. So think of points. Think of a space of points that we're going to search over, and in each point is a potentially infinite list of booleans. You can think of it, if you like, as a list of zeros and ones. That might be a binary expansion for a real number or something like that. But this is the space we're going to search over. And we're going to be interested in properties of these points. So a property of a point is represented just by a function from points to booleans. So some property that's going to be true of some points and not of others. And so the idea is, I give you a property, okay, and you have to answer the question: is there a point with that property? And if there is, can you find one? Okay. Okay. And there are infinitely many of these lists of infinite lists of booleans. There are infinitely many finite lists of booleans, but there are certainly infinitely many infinite lists. Okay. So I'm going to do this. We've got a program here that does this. So we've got this function witness, which you give it a property, and it maybe returns a point. Okay. So if there is a point satisfying that property, it will give you one. If there isn't one, it will just return nothing. So have you all seen this maybe type? Okay. You've seen this maybe type. So it gives you either a point or nothing. Okay? And how does it work? Well, the way it's going to work is going to use this function best try. So best try takes a property and tries to find a point with that property. Okay? And the key point is that if there is a point with that property, it will succeed. It will return a point with that property. If there isn't, it will return some point, which of course won't have that property, but it doesn't matter what point it returns. It will just return something. So it will try the best it can to find a point with that property. And then of course, to see whether that, so then if you apply the property Q to that best try, if there is a point with that property, then this will return true, and the best try is the point. If it isn't, then there isn't one. So how does this best try thing work? So what lasers is going on here? Right, so this is where there's a really mind-mangling recursion. Yeah. Okay, so this, people will find it ordinary. If you're used to the sort of, the mental gymnastics of ordinary recursions, then this is another level up from that in terms of how to get your head around it. So the idea is, so we say, well, let's try a lazy list. Let's try and see if we can find a solution with a list whose head element is true. Okay. So we say, we look at it, one whose head element is true, and then we recursively find the best try for the remainder of the list. If that gives us with something with the property true, then that's what we return. Otherwise, we return, we try the best we can to find one with false at the head of it, and we get that. So, I mean, this looks like it can't possibly work, right? I mean, how does this recursion automatically work? Do you agree? Do you agree with me? This can't possibly work. except that it can. But if you're, so I mean, the reason this can possibly work is that any property Q has the if it really is a true-false property of all binary lists, okay. Any property Q will only inspect the first so many components of this. We don't know how many, but you know it won't go on inspecting the list forever. It will only consume finitely many initial values of this input list. And this program sort of implicitly discovers how much of the input list Q needs to look at. It takes a long time to understand this, but this is a really quite surprising thing. Yeah.
I would say this is more
Property of
laziness.
Yes. It's important that we've got lazy, potentially infinite lists. Yeah, that's true. I'm not saying you can do exhaustive search over every infinite data type. There are certain infinite data types, like this one, of laziness, for which you can do exhaustive search. But that is a really good point. Okay, so we're making use of this particularly evil recursion here. You see, this best try is calling itself in especially weird ways. And it turns out you can prove that this is something that you can't do with just iteration. Okay? So again, interesting computability difference and quite a surprising bit of magic that you can pull off with recursion and not much else. So I find that amusing. Okay, time for the final strange thing, and this is the subject of a paper I've written with a couple of colleagues, Sam Lindley, who's here, and Daniel Hillestrom, who was Sam's PhD student, was here and is still quite often around here. Sometimes. Just a couple of weeks ago, we had our revised version of it accepted, so I'm very pleased about that. So what's the story here? So another kind of difference between programming languages is in the way in which they let us manage the flow of control within a program. In other words, what happens when, which bits of program get run when. So for example, in a very, very pure language, sufficiently pure language, without exceptions or anything like that, there is, once you call a function, it's like this idea of having one line. If you call a function f, then you sort of commit to evaluating that function, and you can't do anything else until f is returned to you. Okay, and then if f returns a value, you can go on and do something else. But you've kind of passed over the baton to this f, and you need to wait for the baton to come back to you before you do anything else. So very restricted control in a very pure functional language. Of course, we know that if a language has exceptions, then other things can happen. So if the function throws an exception, then that means we can jump out of it early without returning a value. Okay, so the evaluation of this function body might not complete. We might sort of jump out prematurely using throw. So we've got more flexibility in the sort of flow of control if we have exceptions. Okay. Going a bit further, if we have not only exceptions but something of roughly the power of coroutines, okay, we can jump out of a function call, okay, but later if we decide we want to resume that function call, carry on from where we left off, we can jump back in again. Okay, so we can sort of switch between being outside the function and being inside it. Okay, so you couldn't do this without something slightly special about coroutines, but with coroutines you can resume the function call from where you left off, And when you jump back into the function call, there'll be a sort of throw expression that was there, and you have the opportunity to supply a value for what the throw expression, if the throw expression hadn't thrown anything, it just evaluated to a value to let you carry on, you have the option of supplying a value to let you carry on. So you can jump in and out, and you can resume things. And then at the most advanced level of all, if we've got a more funky feature like, for example, effect handlers, which is what our paper was about, or multi-shot continuations, these are maybe slightly more exotic language features, you can jump out and you can resume but you, from where you left off. But you can not only resume just once, you can resume multiple times. So you jump out and you can resume multiple times, passing in different values at the point where the throw occurred. So you can resume with a value of 0, and then sometime later see what the function returns, and then later on you say, well, what would have happened if I'd actually resumed with 1 there instead? Then you can do that. So this is quite a slightly exotic thing. So this is a level of power that we don't have in widely used languages like Java and Python. But it is finding its way into new, there are new frameworks. So Daniel Hillstrom, for example, is one of the people who's involved in WebAssembly, and they're getting effect handlers into that. Okay, so there's an upcoming generation of languages and frameworks that will sort of include this sort of thing. Okay, so that's a whole sort of hierarchy of different kinds of languages we have here. So what difference does it make? What can you do if you have these more advanced features that you can't do without them? Okay, so here I'm going to talk about a difference on the complexity side. Okay, I'm going to talk about a little problem, which is quite a simple problem, and the efficiency with which it's possible to solve this problem actually radically depends on what features you have in your language. So again, it's a search problem, and our space of points that we're searching over is basically going to be, so fix an n to start with. Okay, the whole thing is parametric in n. And a point is basically a vector of booleans of length n. Okay, so true, false, false, true, whatever. So there's 2 to the n possible points in the space. Okay? Okay? And we're going to represent them as functions from int to bool. So the 0th coordinate will be the value of a point p at 0. The 1st coordinate will be the value of 1, and so on. So a value p of this type represents this vector. Okay. So now we're interested in properties of points, which again are represented by this type of properties. Property of a point just maps points to booleans. So this is already a second order function, because a point is a first order function, and property is a function that acts on those. And now the problem is this: to write a program, so remember there are 2 to the n points, write a program which we call count, which takes a property, call it q, and tells us how many of the 2 to the n possible points satisfy this q. So this is not too hard to understand. Except it's slightly mind-boggling because this is now a 3rd order function. Okay, it's a function acting on functions that act on functions. So this might start to make you feel a bit ill. But other than that, I mean, it's clear enough what we're trying to do here. So okay, so just before, okay, I'll try and wrap up fairly. I've got 2 more slides, I think. Okay, so just before I explain. What difference it makes what language you're in. Let's think about how properties can behave. So here's a sample property. So this q takes a point p, which is, let's say, a vector of length 3. It looks at component 1, and if component 1 is true, then it does p0 and p2. Otherwise it does p2 or p0. So what this is doing, we can represent by this sort of decision tree. So first it sort of queries its argument at index 1, so that's indicated by that first thing. And then it branches according to whether the result's true or false. If it's true, then we're in the then branch of the if clause. The next thing it does is it queries P at position at index 0. Because we're doing an AND, if it's false, we can return false straight away, saying this is interpreting this as a short circuit AND. If it's true, we need to go on and evaluate the argument at index 2, and then we can return true or false. So there's exclamation mark, trues or false at the leaves. At the leaves we have return values, which are what our queue is going to return, either true or false. The question values, the internal nodes are questions we put to P, and the branch values are the branch true or false are the values that P gives back. And likewise here, we can do it on this branch. If query 1 returns false, then we ask query 2, and then we ask query 0. So the order in which we ask queries to P might vary from one part of the tree to another, okay, depending on, so this illustrates that, depending on the results of earlier queries. And note that sometimes, as in here and here, Q can return early in the sense that it can return without having inspected all the components of P. So in these cases it does inspect all 3 components of P, but doesn't always have to. So that's the way to think about these properties. So yeah, now let's look at what the differences are between languages. So our seemingly simple problem is interesting because it shows up some genuine complexity differences between the languages. So simplifying a bit. If you're in a very restricted language with iteration but no recursion, there's basically nothing you can do that's better than trying all to the endpoints in turn and then just counting them. Okay, so you just cycle your way through all the points. Very boring. Any decent language will support that. Okay, it doesn't mean anything clever at all. Okay. Now, what might be surprising is if you've got recursion present, and pure Haskell will be enough for this, we can actually do a bit better. We can actually prune the search in parts of the tree where false is returned early. Okay? So if we get a false returned early, the idea is that we sort of know that there won't be any, the count for that portion of the tree, that whole portion of the tree will be 0. So whatever whatever the values of the components that we haven't looked at yet, the value will be false anyway. So we can.
And you're doing this by instrumenting the point function?
No. This is just by a recursion trick, similar to the infinite search recursion trick. Sorry, maybe I misunderstood what you were asking.
I'm asking, do you have to know which parts of the point the predicate is looking at?
No, it discovers that. It discovers that itself.
No, I mean, as part of the algorithm, you have to be looking at that as you're running the algorithm.
The algorithm implicitly discovers which bits aren't looked at by the fact that it doesn't.
Right. So it has to be checking which parts of the point the predicate is accessing.
Implicitly, yes, but it doesn't.
Basically, what I'm asking is, you can't treat the predicate as a black box.
Depends what you mean. Well, the predicate is a black box, but it's a nestable black box.
Yeah.
It's a black box. It's a black. The predicate is a black box. The things that you feed into the predicate, you smuggle in recursion calls to the predicate.
Now I understand how this can work.
Right. Okay. It's like the infinite search thing. It's a surprising but clever trick. But there's no explicit detection. Yeah, there's no explicit detection of did I look at this component or not. But if we go on to this one, if you have mutable state in your language, then you can do what I think you may have been. You can do something like you can smuggle in a stateful point into a predicate. You can actually here explicitly detect which components you look at and which you don't. And in this case, you can do pruning on both. If either true or false is returned early, then you get a win. If false is returned, then you have a 0 contribution. If true is returned, then you have a 2 to the something any extension of that will be will give you a true, so you can have 2 to the something or other straight away. Okay. Okay. So the more we have in our language, the better we can do. But these optimizations only apply in the case where there's an early return. Okay, either true or false. If our predicate is of the kind that always looks at all n components, then this is still no better than just trying all the points in turn. And you can actually show that in these kinds of languages, the runtime can't be better than n times 2 to the n. So 2 to the n because that's how many points there are, and n because for each point we have to inspect all of its components in this situation. However, if we have effect handlers or something similar, one of these advanced control features, we can get a genuine speed up. Okay, we can bring this runtime n times 2 to the n down to 2 to the n. So we've got genuine asymptotic gain here. How does this work? Okay. So the idea is, suppose when we think about applying this predicate to a vector true, 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 and then to the vector true, true, false. So in the first case, you'll follow your way down here. The second case, you'll follow the way down here. And then you can notice that those computations proceeded identically up to the point where you interrogated this value. And then it sort of went different because you've got true in one case, false in the other. So what we'd like to be able to do is to sort of capture the state of the computation at precisely this point, okay? So that we can then resume the computation with supplying true there, see what happens. And then say, well, what would have happened if I'd done false there? So that would then mean without repeating the journey particularly down to this node, you can just redo this last bit, okay? And of course, once we've done that, we want to back up to this node. And we want, if we've also captured the state of computation at this node, we can resume at this point, and instead of saying, what? And say, well, last time we gave true as a result of that. What would have happened if we'd given false? So the idea is that all the nodes we visited, wherever we're at in the tree, we've got a stack of all the nodes we visited. And for each of those, we have a state of computation kind of captured, which we can resume if we want to, with a different value. And that means we don't have to sort of keep starting from the root every time we want to inspect a new. Yeah.
What does this do to the space complexity?
Space complexity. That's a very good question, and it depends largely on how you implement the. Yeah, you're probably asking that because you're thinking about all these computation states. There are different implementation strategies for the capturing these continuations and stuff. So it's a bit. But there are. If you do it right, it's not too bad. There's a class of situations where it's quite modest. I can show you the paper if you want to see more. We do discuss the space complexity briefly in the paper. But yes, time complexity. The main headline is that time complexity comes down from n times 2n to just 2n. So that's again a third example of a non-trivial and actually quite fundamental difference that it makes between the kinds of languages that have this gadgetry in it and the kinds of languages that don't. There's a genuine fundamental difference in complexity. So, are all programming languages equally powerful? So, to sum up, for bog standard computation, the answer is basically yes. There's that minor wrinkle about efficiency in Haskell, coin changing in Haskell, but basically the answer is yes, both for computability and complexity. For higher order computations, definitely not. So as we've seen, there are some quite profound differences between programming languages, both in terms of computability and complexity. Now, of course, that's not necessarily a disadvantage of weaker languages over the stronger ones, because devotees of Haskell and so on might well point out that that fact might well be offset by other advantages of using weaker languages. For example, simplicity of reasoning about programs. You know, the less the less mischief programs can get up to, the easier it is, the fewer things you have to worry about when you're reasoning about them. So this isn't to say, you know, stronger languages are better, but these differences, I would say, are surely part of what we want to be aware of in terms of sort of weighing up one language against another. So thank you very much for listening.
So I think this is working? Not yet? Oh, there we go. Good. We use this for questions, so.
What's the most powerful programming language?
The most powerful programming. That is a very good question. You could say the most powerful programming language is Lisp, because Lisp has a thing called quote. So what quote lets you do is, you know, anything I pass you, you can turn it back into code. Right, so you can see the underlying code for anything I give you. So in that sense, all this higher order computation then gets flattened right down to bog standard computation, because if you can actually see the underlying code for anything I give you, you can do anything you like just by simulating. So that's one answer to the question, but it's hard to it's surprisingly hard to make that question really precise. Actually, it's a good question.
So, Chris.
Yes.
Can you get that?
Yeah.
Yay!
Well impressed.
Can you go back to the slide where you had a tree?
Yeah.
Yeah, I was wondering if in a programming language with just recursion and mutable state, if you could put one step of that tree traversal as a function, and then keep the state, say which state you were in and what the result was, would that be a valid replacement for the programming language feature that you were talking about in this lecture? Or is there something that's specific?
That's kind of, if you have that feature, that is kind of the essence of what you have. That feature, if you can capture a state, that's basically what multi-shot continuations are. You can capture a computation state, and then you can resume it multiple times. That's basically what it amounts to. Yeah, it's.
So would you say that the advantage of the feature that you just introduced is that more syntactic, that it's easier to do, or is
Oh, right. You're asking what would be the difference, the advantage of effect handlers over multi-shot continuations? Yeah, it's more that they're a bit more abstract. Effect handlers are a bit more abstract. That would be more a stylistic difference than an expressivity difference. But yeah, so I would say they're a bit more abstract, a bit easier to reason about. There's a nice general story of, there's a general conceptual story that they fit into.
Okay, thank you.
Yeah.
So I don't really deal with all the programming language theory, so this is my first time learning about all this. But is it possible to find in the future a more powerful notion after effect handlers and multi-shot continuation?
Again, that's really it is possible. One can dream up artificial examples of language constructs that will give you even a bit more power, but I don't know of any convincing argument that they would be useful for anything. Whereas, effect handlers were arrived at for quite different motivations. This wasn't the motivation for introducing effect handlers. It sort of came out for other reasons, and then sort of we noticed, actually there is this fundamental efficiency difference. In principle, there's no theoretical reason I know about why someone in the future might not go a step further.
Okay, thank you very much.
I guess I have a question actually. So in that sort of hierarchy of new features you can add to get more, be able to compute more things, where does non-determinism fit in there?
Oh right, very good. Yeah, I've left that out. That's kind of a bit orthogonal to all of this. Yes, it's a good question. It is another example of a. Well, yeah, I suppose you could say if you bring non-determinism into the picture, then even at the bog standard level, computation. I've been implicitly talking about deterministic computations the whole time. So yeah, that is another axis on which programming language may vary. A bit orthogonal to what I've been talking about.
Would you get more? Would you be able to compute more things, or would it just be a speed improvement?
You can't really compute. Again, so all these questions, there are sort of multiple ways of making them precise.
Sure.
One way, just picking one at random. So adding non-determinism to language doesn't let you compute any more deterministic functions than you originally could, because you could just replace your non-deterministic, operator by something that just always, if you do a coin toss, you just say, well, plug in a function that just always returns heads or something, because that's one possible behavior of a non-deterministic process. One possible behavior of a non-deterministic process is to behave deterministically in a certain way. So in some sense, it doesn't give you any interesting power, but there are other, it's not entirely as simple as that either. So.
Okay, thank you. Anyone else? No. Right, in that case, thank you again.
Thank you all for the questions.
So in the room behind you, there's pizzas ready and some drinks. So feel free to keep going.
Could I just say that I did say I would have copies of my book for sale? That is true, and you can buy one, but I only have 2. So if you're desperate, I'll have more on their way, but if I'm happy to sign for it or just let you look at it, whatever.
You can just mute and something cover.
can change them like midway through if you want.
So it'll be like more dramatic.
Yeah.
That's all I have to turn it down.
It doesn't make sense that the higher numbers would be down on that thing.
Wait, number 4 is really good. I think it's just like a light.
Number 4 is good.
Is it an intense light?
Yeah, it's quite. It's low. If you let it go down.
Oh.
It's a good intensity. Or maybe you could do so much.
No, it's not. The co-pilot is so good. The co-pilot Claude, Gemini, ChatGPT complex. No,